full house now, so let's go. Oh damn, wait, I misclicked. Okay, so we're going to do some of the questions that basically you will see in this. So they're very similar to what we've been doing previously. Let's just look at them. So for the very first question, an example, it says that there is a 12 nanocoulomb charge and 4.5 nanocoulomb. Oh, sorry. In fact, let's not do nano, it will be too small. Microcoulomb, 4.5 microcoulomb charge with a distance of 24 centimeter. So first part, it says determine the null point. Okay, when they say 12 in this, so we will automatically assume that he's talking about positive charges, because otherwise he would write negative. Okay, so first let's just make let me just close app and redo it. Glitches sometime. Okay, so it says determine the null point, so we're going to basically draw this. So there's a big charge, there is a small charge, and then the distance between these two is 24 centimeter. At some point, of course, there is going to be a null point, and at the null point we have a test charge placed, say Q. This is positive charge, this is positive charge, this is 4.5 microcoulomb, this is 12 microcoulomb. So what we need is, we need to find this distance r, and for this distance, if this is r, then we can say, okay, this distance would be 24 minus r. Is it clear, everyone?
Yes, sir.
Now, now, so we should understand at the null point, the force on this from, say, let's call this Q, and let's call this small q. So the force of Q will be equal to the force of small q, because that's what null point means, and same goes for the electric field, because electric field strength, if it's same, then basically it appears to be a null point. So you can keep either force or electric field strength, doesn't matter, so you write E1 equals to E2. Now electric field strength formula is K Q over R1 square, and here we're going to write K Q over R2 square. Is it clear? Now this basically K's cancel out, which leave us with only these two things, which means Q, which is 12 times 10 raised to power minus 6 coulombs, R1 is basically 24 minus R square, that is 4.5 times 10 raised to minus 6 coulombs, and that is R square, right? Generally, when this sort of situation comes, I would just basically would like to take a root on both sides. The reason for taking the root is that here I'm getting an a minus b whole square function as maths, and I don't want a quadratic equation to form. So what will I do? I will take a root on this side and a root on this side. This will basically give us under root 12 over 24 minus r, and this will be 4.5 under root over just r. Now things become really simple, and you can simply multiply, cross multiply, and solve this. So when you solve this, you should expect an answer of 9 centimeters. Is it clear, everybody?
So why did you equate E1 and E2?
Because at the null point, you should remember that the net electric field here, net electric field strength is 0. Also, the net force is 0 because they're vector quantities, so both charges are equally pulling each other like that. Is it clear?
Yeah, that's right.
So if they're equal, so we can put them as equal. So if this is 9, I'm just answering, and I'm writing if this is 9, then we could say that this would be 15 centimeter, because 24 minus 9 is 15, right? Okay, so the next question is a better one, basically part B. So in part B, it says that a 2 nanocoulomb charge is moved from midpoint to null point. So it says determine the work done to move to n from m, and they've also given the diagram. So let me just I need to redraw actually. Alhamdulillah, I'm sorry. Okay, this is annoying me. Alhamdulillah. Okay, so there is this charge, and then there is a small charge just right in the middle, and this is the null point, and the rest of the things are same. This is m, and this is point n. Okay, now so this distance from here to here, we already know it's 25 centimeters. Then from this to the middle, we have oh, it was 24, sorry. This is 12 then, from the middle, right here, and the null point from here was 15, and from here to here it was just 9 centimeter. We did it in the previous part. Alright, everybody understand this? The value for this is 12 microcoulomb positive. This is 2 nanocoulomb positive. This is 4.5 microcoulomb positive. Now what they're saying is they wanted to move from this point to this point, and they want us to find the work done. Do you guys understand the question at least?
Yes, sir.
Now, whenever this type of question comes, where there are two charges or three or whatever, no matter how many. So, if you got to go from one point to another, you got to find potentials on both points. So, first of all, we are going to look at step 1. Step 1 would be that find the net potential G. पढ़ा हुआ है हाँ Okay, so find V net at M. Okay, so we're going to find the total potential at this point. Now, the voltage or the potential at M is due to the two big charges. So this was, let's call this Q1, just to change the way you guys think, just to do that. So the potential at M due to Q1 plus the potential at M due to Q2. Do you guys understand? These are just symbols, they're not divided. Okay, now what you're going to do is, the potential value is K Q1 over R1 plus K Q2 over R2. Now let's add in the values and see what you get. So for this one, K, I'm just going to take, because K is common in both, I'm going to take it outside. I'm going to write 8.99 times 10 raised to 9 just to save some time. Q1 is 12 times 10 raised to a minus 6 coulombs divided by, till the midpoint the distance is 12 centimeters, so I'm going to write 0.12. Why 0.12? Because I've changed it to meters. Plus the other one is 4.5 times 10 raised to a minus 6 divided by 0.12 because it's the midpoint. Any questions here? Okay, so then what you guys need to do is that find the value, please. Put in the calculator, find the value, please.
So is it 1.2 into 10 raised to 6?
Yes, that's correct. So basically it is 1.24 times 10 raised per 6 joules per coulomb. Now this is the step 1, right? Now I'm doing the step 2 in a different color so that you guys can differentiate it. So step 2 would be find V net at N, because you want to go to that place, so you should know the potential at that point. So voltage at N will be equal to the voltage at N due to Q1 plus voltage at N due to Q2, because these are the two big charges affecting that point. Now let's write the equations. K Q1 R1 plus K Q2 R2. Okay, now what you're going to do, take K outside, so 8.99 times 10 raised to 9, and then let's make the equation. So Q1 was 12 times 10 raised to minus 6 divided by, the distance was 0.15 till the null point, plus other one was 4.5 times 10 raised to minus 6 divided by 0.09. Any questions? Zero 0.09 because I converted 9 centimeter to that. Okay, when you try to attempt finding this, please just check whether my calculations are correct. It should be 1.17 times 10 raised to power 6 joules per coulomb.
Yes, sir, it's correct.
All right. Fatma, Aman, Gatika, and Rafi, do you guys understand this?
Yes, I got it.
So when you have the
Yes.
potential of both sides, so in the step 3, with a different color I'm trying, step 3 would be find the change in potential. Now when you're finding the change in potential, always remember, because potential is a scalar quantity, so you always need to do bigger minus the smaller value. Okay, that's the way to deal with scalars. So what you're going to do, you're going to find the change in potential. Change in potential is basically the bigger value amongst these is at m, right? So we're going to say, okay, we're going to subtract Vm minus Vn. So 1.24 times 10 raised to power 6 minus 1.17 times 10 raised to power 6. This should give you 1.4 times 10 raised to power sorry, now this 0.07 times 10 raised to power 6 joules per coulomb. Please check if I've done it correctly. All right.
Yes, sir, it's correct.
Then step 4, which color should I use? Okay. So step 4 should be that you use work done equals to voltage times the charge that you're moving. Okay. I'm also writing charge that moves. Okay. So with that work done, the change in voltage was 0.07 times 10 raised to power 6 multiplied by the charge, which was basically 2 nanocoulomb. So 2 nano is 10 raised to minus 9. So can you guys tell me what would be the answer? Is it this? 1.4 times
Yes.
10 raised to minus 4 joules. So these are the 4 steps to deal with any question that basically asks you to find change in potential or work done at the end. All right, I hope you guys understand this. Right, now going forward, we're going to basically do some rote learning, because he's going to ask us the difference between electric and gravitational fields. Difference between electric and gravitational fields. Okay, for this one, basically you just need to learn this. There's no other way, because they can ask you anything from it. So we're going to write the quantity that we are comparing, and then we're going to look at what happens of that quantity in gravitational field and then electric field. So number 1 is the type, number 2 is the law, number 3 is the force, number 4 is the work done, number 5 is the potential, Number 6 is the field strength. Number 7 is the direction of field. So basically these are the 7 things we are going to compare. So for gravitational fields, the type is that it is attractive field, and electric field is repulsive and can be attractive as well. Okay, that's a similarity and a difference both. Law Newton's law of gravitation. In this one it is the Coulomb's law. In gravitational field, the force is taken out by Gm over r square, and in this one the force is taken out by q over 4 pi epsilon r square. Is it clear, everybody? Or you could say kq over r square. It's the same thing. The work done is Gm over r, and in this one it is kq over r, very similar. Potential is the symbol of potential in gravitation is this, which is work done per unit mass, or minus Gm over r. In this one it could be voltage is work done per unit charge, and it is equivalent to plus minus kq over r. Why did I write plus minus? Because for positive charges it is plus, for a negative charge it is negative. Then the field strength, which is given by G, force per unit mass, or Gm upon r square, right? And here it is force per unit charge, and it is equal to kq over r square. Then comes the direction of field. Direction of field is basically determined by the path taken by a unit stationary mass placed in the field, and this is the path taken by unit positive, and this is very important to remember, positive charge taken by unit positive charge when placed in the field. Everybody understands this?
Sir, how did you get the formula for work done in electric field?
The same way. Okay, I'll tell you in a bit. Okay, don't worry.
Okay.
All right, now basically we just need to do a couple of graphs. So please put the heading. The difference between solid conducting sphere and non.
Okay.
Yes.
Can you go up a bit so take a screenshot of the above one?
Yeah. So in 10 minutes time, please When the meeting ends, you got to rejoin. Now, so the difference between solid conducting and non-conducting sphere. So for a non-conducting sphere, I just want to tell you, let me just draw this once. So a non-conducting sphere is just like an insulator or something, right? The main thing about that is that if I place the insulator here and we are looking at voltage, okay, let me copy this first, use it again and again. Okay, so if I want to draw for say voltage in joules per coulomb, potential, and R in meters. So we already know in the solid conducting sphere what happens is when it is charged, the charges spread evenly throughout the whole sphere like this, okay? And the method of charging we don't need to know, but you might have remembered from O levels that you used to, rub it against a woolen cloth or something, okay? So this basically shows you a curve like this because voltage is inversely proportional to 1 upon R. However, from the inside, the voltage increases non-linearly like this. Let me draw it a bit nicely like this. So inside it is this, and this is basically the radius of the sphere itself. You got to remember this. Usually this non-conducting sphere graph hardly ever comes, so you don't have to worry about it. Then for the electric field, the same graph for electric field strength in Newton per coulomb, R meters. How do you draw this? So it would basically show you the same charge. The charge is basically evenly divided throughout the whole sphere. So electric field strength shows you a sharper bend. The reason is that electric field strength is dependent on 1 upon R square, but inside it is basically a straight line like this. It increases, and this is the radius. Till the radius it increases and then decreases outside. So please draw this, and then we're going to talk about the one that will always be there.
Sir, do we need to know why it is straight inside and then there's a curve outside?
No, you don't need to know.
Okay.
You just need to basically know that the shapes are like this, okay? Basically it involves integration. You know integration?
No, sir.
You don't take maths, right? Who knows?
I don't.
Who takes maths and knows about integration?
So I do.
Yeah, okay. So integration is a part of calculus in math, and unfortunately and fortunately, major part of calculus is not part of our syllabus. That's why we don't get into these things, right? Now, the next thing is solid conducting sphere, and when it is a metal. Of course, metals are conducting, that's fine. So these have a different, basically, way. So in a solid conducting sphere, what happens is the charges, you know about free electrons and stuff. So basically they don't stay at the center, but they just gather at the edges. Because,
Say,
yes, yes,
why do we make the circle on the y-axis?
just to show where the radius is. Nothing important, okay? Just to show where the radius is. Understood?
Got it.
Now, in a solid metal sphere, the difference between those two is that in a metal sphere, because we have freely moving charges, they can gather at the ends. So, basically, because they repel each other, they don't want to, stay there. So, when they gather at the end, you guys need to remember that the potential, basically stays constant till the radius comes, right? So this is the radius. The potential stays constant, and then it decreases the same way as the potential does, because V is equal to proportional to 1 upon R. So this is very, very important, because this will come a lot of times, okay? Then if we want to draw the electric field strength graph for this, so which is easy, because you can just draw the gradient. This is E, Newton per coulomb. This is R, meters. So because it is a flat line, the gradient is 0. So till oh my god, till the radius, potential remains 0. Then it basically goes up, and from here it decreases sharply. So this is E will stay 0 here. Is it clear, everybody? Now these two graphs are very important, because generally these comes, okay? And when we will solve the topicals, you'll see a lot of questions related to these, and they will also ask you to draw these, so you got to remember that. Okay, now the last part, you guys have done it. Anything you want to ask, please let me know. Okay, now the last thing in this chapter is really small. It's called the concept of the distance of closest approach. The concept of the distance of closest approach basically works from electric work done. So this is basically what Gatika asked, how did I get the work done formula, or the thing. The reason is that work done is given by change in potential times charge, right, Gatika? So change in potential is kq over r times charge. So when you multiply this, the work done becomes kq q over r. That's how we got the formula there, right? Now, do you guys know about fusion? What exactly that is? Nobody knows about fusion? That's very strange.
It's
Fusion?
a type of heat transfer.
No.
What type of fusion, sir?
Nuclear fusion.
It's when two different nuclei combine.
Yeah, combined, right? Now keep that in mind. When the meeting ends, we rejoin. We're going to talk about it. Okay, so you guys are here. Ishmiya, okay, Aman, we gotta wait a couple minutes. Okay, now, so I was saying that have you ever realized that to fuse two nuclei, when you say nuclei, it basically means you're fusing two big positive charges, right? Because nucleus is just positive, right? And to fuse it, you need to bring them closest to each other so they can touch and then they can fuse. And to do that, you need to overcome the repulsive force that they have between each other. Don't you guys think? So, what I mean by that is that suppose there is a big nucleus, gold, which has 197 mass number and proton number as 79, and then it has, suppose we want to fuse helium, which has 4 mass 2 charge, and you send it to with a velocity towards this with 10 raised to power 5 meters per second, and we want to know exactly where it goes, how close it can go, because it is also facing a force of repulsion because of the both being positive. Now what we're really looking at is that how close that nucleus gets to the other nucleus. So this is the concept of closest approach. Is it clear, everybody?
Sir, could you repeat, please?
Yes. So you see, helium is a positive. Helium nucleus is positive. We all agree to that. Okay. So we are saying, what I'm saying is that both of them have a repulsive force between them because positive repels positive, right?
Yes, sir.
If the positive repels positive, then it would mean that when you throw it towards it, it is going to retard, it's going to slow down, right? And there will be a point where, because of that retarding force, it will stop, right? So the closest approach would mean how close it gets to the other nucleus, right? Is it clear?